Thanks everyone for joining. I know this is the last session and everyone's probably pretty wiped. A lot of good info, hopefully, that from other sessions today and the great keynotes we had this morning. So this session is called Lessons from the Field. I call it Episode 2. If you were at Spark Summit in Dublin last year, I did another version of this talk. So this is basically a continuation of that with some new information. So a little bit about myself. Like Nick said, I'm a resident solutions architect with Databricks. I've been with Databricks a little over 2.5 years. I've been working with Spark much longer than that, though. I started with Spark pretty early on, in the early days before even it was an Apache project back in 2012. And my job as a RSA at Databricks is basically working with our customers. Some are new to Spark, some have been using Spark for quite a while. And what I felt was like it'd be good to kind of combine a lot of the lessons I see from the field working with these customers and some of the issues that they hit in their applications and try to give some best practices on that. If you're interested in my talk from last year, it's on YouTube. There's the link there you can go to as well. So, building Spark applications, there's a lot involved. But what I feel that's important, there's like 3 main things that I personally feel are important to really get a good understanding on in order to build more reliable and better performing Spark applications. So, the main thing is file formats. What are the data sources that you're using? Understanding the pros and cons of those data sources. What situation they work best in. Partitioning, shuffling, and parallelization, right? Spark being a distributed framework, understanding how it takes the data sources that you're reading, how are they distributed, when you're doing any sort of aggregations, joins, things like that, how does shuffling come into play, how can it impact your applications, and then finally, how do you manage parallelization, right, across your cluster. And then one of the most important things that I always focus on with users that I'm working with is how to use the tools available to you in the Spark UI and query plans to help you debug, tune, identify issues in your Spark applications, and give you a better understanding of what's going on under the covers. So, first in terms of file formats, right? Spark itself supports CSV, text, JSON, Parquet, Avro, Orc, right? There's a bunch of others. Then there's third-party external data sources. And so all these have different benefits and trade-offs. So it's important to understand what those are and when it's appropriate to use certain data sources. So working with a lot of new users coming to Spark, especially people coming from like single-node Python or single-node R, what I find is a lot of the data sources that they're used to are CSV, right? But working on CSV data that fits on a single node with something like pandas or DataFrames, right? They have great support for that, and that's great. And they're very easy to work with. But when you're starting to move to much larger data volume and distributed processing with Spark, it's important to understand how Spark treats those text data sources and how that can impact your application. So, first, how does Spark actually read like CSV data? So, CSV data obviously is just raw text on storage. So you're going to have, it may be compressed or uncompressed, right? But essentially what's happening under the covers is Spark reads line by line, reads the data as a Java string, then takes that string, it does some sort of tokenization based on your delimiter. And then finally, based on the schema for that data set, for that data frame, it then has to cast those strings into actual Spark data types. So, for instance, this text data, there's maybe some integers, there's some strings, there's a date value, right? So internally, Spark, treats a date value using a number, based on number of days, and then there's either a double or a decimal, right? So every time you're accessing that CSV data set, it's going through this process, okay? And with extremely large volume CSV files, this can start impacting the performance of your job. So a few ways that these issues can manifest is, one, it can be slow to start up your job. So this can happen if you're using what's called infer schema. So this is where Spark will essentially scan your data set to figure out what are the appropriate types for the columns in the data set. And in order to do that, it needs to do a full scan of the data set. Now, it's one thing to do that on a 1 meg file, 10 meg file, but if you're trying to do this on hundreds of gigs or terabytes of CSV data, basically you're going to be spending minutes, potentially even hours before you can even do any queries. The other thing is something that I'm sure if you've been in the big data space that you're already familiar with this, is splittable compression schemes, right? So if you're dealing with very large gzip compressed text files, they're not splittable, meaning if you have one file that's like 100 gigs in size, that's gzip compressed, Spark, doesn't matter how many cores you throw at it, it'll use one core to read that file in. So, I've had situations where customers, came to me and said, we're having really, bad performance, the job is failing, we have all these issues, and if you look at the data set that they're trying to load, I've seen in some cases hundreds to 200 gig gzip CSV files. So that does happen, and so you have to be aware that the issue really isn't within Spark itself, but with your data source. So the other thing that can happen is dealing with very wide CSV files. Here, what I mean is you're looking at CSV files that have hundreds, I've seen even thousands of columns, okay? And so again, if you think back to the step before of how Spark is reading that data, there can be issues with like garbage collection due to the number of objects that are getting created, all the casting that's happening and converting to Spark data types. So one thing, because it's a text format, you don't get the same like predicate push down and things like that you would get with Parquet. Now, luckily, there's a feature that's coming out in Spark 2.4 that will help this a little bit, where it'll actually do column pruning as it's loading the data. And that helps a lot. I've seen it help, especially with garbage collection issues. So here's an example where with column pruning off, loading 2 columns out of a data set with 200 columns, the task with column pruning off, we're basically spending half of a second just doing garbage collection, just due to the number of objects that were getting generated. With column pruning on, that got cut down significantly. So going back to the schema inference, so the infer schema option, if you enable that when you load a CSV data set, again, it has to scan the full data set. So that's really a performance killer. So another option is, of course, you could just disable it. You could just say infer schema false, and everything comes in as a string. But that's not really a good practice, right? Realistically, you're going to have numerical values, dates, things like that, timestamps, right? You want to have the actual data types that you're dealing with. So you can specify your own schema, or you can use data source tables. And I go into a lot more detail on this in my talk from last year, so definitely recommend looking at that. But if you are going to specify your schema, it's important to be precise, right? Again, don't just set everything as string or doubles and things like that without thinking about the impact, again, to your job. So as an example, if you're treating everything either as a string or double or decimal, so in a particular data set where these values were actually decimal values, and you're doing some sort of aggregation, that will actually impact the amount of shuffle data that's being generated from your job, okay, based on the data types that you're defining for Spark, how to treat that data set. With JSON, JSON also will do a full scan of the data in order to infer the schema. JSON does have an option, though, where you can set a sampling ratio to reduce the amount of records that it'll scan to figure out the schema. But again, if you can specify the schema ahead of time, and that'll save you time starting up your job. Now, with Parquet data, Parquet and Orc, they're self-describing, right? So the data, the file, the metadata in the files describe the columns, the data types, and so forth. But still, if you do a Spark read.load, Spark still needs to figure out what's the schema contained within those files. So for older Parquet data sets that were written either with older versions of Spark or with other systems, there may be a metadata path that Spark can look into and pull the schema from. If that's not there, what it'll do is it'll read the first file in the path that you're loading and then pull the schema from there. So that'll be pretty quick. However, there's also an option called merge schema. And this is, if you have like schema evolution, right, where you have, new columns that are getting appended to a data set, there's an option called merge schema where Spark will basically figure out the union of the columns, right, of all the data types. But you have to be aware what's going to happen there if you use that every time you load your data set is Spark needs to actually read all the footers from all the Parquet files. And it's also going to do some validation to make sure that there's, the types are compatible. But that can lead, again, to a slow startup time before you can even actually do any queries if you have, potentially thousands, hundreds of thousands of Parquet files, because what's going to happen is Spark will have to kick off a job and try to read these schemas in parallel. And then finally, combine that into an actual Spark schema format. So again, the recommendation is if you can, use schemas, right? Specify the schema ahead of time, or use data source tables. And if you do have schema evolution, you can, basically add columns to the data source table. With Orc, Orc does not support merge schema. I believe there's a Jira open for that. So there, basically, it'll do similar to Parquet. It'll basically read the first file, read the schema from there, or of course, you can specify the schema yourself. So, once you get past the part of actually loading your data, you're doing some sort of ETL. We always hear like Parquet is like the recommended file format, and it's the default file format for Spark. And there's a few reasons. I'm sure you've heard, right? It's a columnar format. It's using dictionary encoding, all these great things. But also an important aspect is that it's actually maintaining metadata related to the columns that are getting written out. And so that metadata is things like min, max, and count. And those can be used by Spark when you're filtering. So if you have different multiple Parquet files on storage, and you're applying some sort of filter, then Spark can go and figure out which files does it actually need to load and which row groups does it actually need to load based on your predicates. But it's really most effective on sorted data, right? If your filtering key is randomly distributed, then as Spark loads the data, it might have to hit more files than if you just sort the data as you're writing to disk, right? If it's sorted, then your keys are going to be ordered, and then if you do some sort of filter, then it can go specifically load the files where the filter predicates are actually in. So that'll help reduce data reads from storage by obviously skipping unnecessary files. So this is an example of what it looks like, right? So here, this is a 10 million record data set. So on the left-hand side, there's the unsorted data set. Now, while the keys were just written randomly, however, based on the input data, from 10 million, it cut it down to 1 million, 1.1 million records that it read from Parquet. And then finally, Spark applied a filter and cut that down to the 100 records that I was actually interested in, okay? Now, the sorted data set, when the data set was written out, it basically I just did an order by and then wrote it out, order by ID. So what it did there is it actually only had to read 34,000 records from the Parquet file, or multiple files. And then from those 34,000, it then filtered down to 100. Okay, so a couple important things is, one, the amount of data that had to be read in from the unsorted data was a little over 200 megs. And the sorted data was cut down to 12 megs, right? And the duration, of course, you're loading less data, but then you also have fewer records that need to be filtered by Spark, which will help with the execution speed. Now, there are some challenges with this. One, it can depend on your data, but typically you're probably only going to see it really effective on a single sort key. And you also need to be careful with data skew, right? So, if you have something like account ID, right? You have certain accounts that are more active than others, so you may end up with, files that have a lot more records based on the sort key than others. But another really important part is, how do you maintain this going forward? Like, it's one thing to say, oh yeah, just sort your data and then don't touch it, but I doubt many of you have, static data sets. Some of you are probably dealing with streaming data, right? So if you're streaming data, even hourly, right? You're writing new files, you're appending new data. You can sort those new records, but now you're just ending up with a bunch of small files. They may be sorted, but now Spark is still going to have to read a bunch of files based on your filter predicates. So you would have to do something like compaction, and then you have to compact the data and then resort it and then replace the data again and again, and that can be a really brittle and difficult process to maintain. So for those reasons, I recommend reading a really great blog post by one of our engineers on how we do this with Databricks Delta. So the ordering is actually using what's called z-order clustering, which is a lot more sophisticated than simply ordering. And it works well with multiple predicates, like filter keys. And it also helps you manage the data as new data arrives to do that compaction in an ACID manner with ACID transactions and doing it in place without impacting your consumers. So the other part is, how does Spark parallelize your queries based on the file formats that you're reading? So starting with Spark 2.0, there's an internal configuration called max partition bytes. It defaults to 128 megs. So what will happen is when you're processing a data set, what Spark will try to do is it'll try to make partitions within Spark 128 megs in size. Now, this is only going to work with splittable data type or file formats, again. So, if you have, again, an extremely large gzip file, basically non-splittable files that are over 128 megs, it's not going to be able to reduce those in size, okay? So if you have uncompressed text data, you have Parquet formats, then it'll try to fit them within 128 megs. What's really useful, though, is that for smaller files, it'll do what's called bin packing. So it's going to combine files to try to fit within the 128 meg limit. And so this is much better than in the Spark 1x days, where you would basically get one task per file regardless of the size of the file, right? So you could have maybe one file that was 1K in size, another file that was larger than that, and you would get all these individual tasks that were dealing with a lot of small data. So this is like a way of basically doing compaction almost in place as you're reading it, versus you having to worry about like repartitioning or coalescing in your job. So the important thing, though, is to remember that it's based on file size. So there may be some situations where if you have a highly compressed data set, with low cardinality, then the file size may be much smaller than you actually expect once it's decoded and decompressed. So if you have queries, ETL jobs, you're doing any sort of processing, and you want to control either the size of the partitions or the size of the output as you're writing data out, there's a few ways that you can do that. So, you may be worried about, how do you manage file sizes in like an ETL job? Maybe you're processing, you're taking data from like text data and then processing it and then saving out as Parquet. Or you may have some queries that are like generating rows, right? So these are, where you're doing things like explode or flat map or broadcast joins, right? So you have data that's coming in that's maybe, X size, but then you're multiplying it by, 10x, 4x, right? So your partitions coming into your query are one size, but then they come out much larger, and you want to control that. So typically what people have done is they say, well, I'm going to repartition my data set when I load it, and it'll redistribute it, maybe in smaller partitions across the cluster, and then I'll continue on with my processing. But right away, what you've done is if you've introduced another shuffle stage in your job that's not necessarily needed, right? And a shuffle stage is basically going to introduce I/O, network I/O, file I/O, and having to move the data across the cluster. So another thing you can consider is basically tweaking the max partition bytes. So I had a situation where I had a customer that had some R code that they were needing to basically distribute, right? So it was single node R code, but they've gotten to the point that their data size was too large to process on a single node. So they wanted to do this with Spark. And because of the way that their algorithm was running, it was basically exploding the data set significantly. And basically the R process was dying due to the amount of data. So again, the first thing he thought was, well, I'll just repartition the data and then make it smaller and then feed it into that R UDF. But by just tweaking this max partition bytes, we were able to do it without any shuffles. And this was basically, it turned from a really slow job with the repartition and so forth into a single stage job that completed in seconds because of that. The other thing is, as you're writing data out, you may want to control the file size again. And so another option there is on output is max records per file. So what you can do there is basically set a cap on the number of records that you want to write out. And then each task, as it's writing data out, will basically keep a counter. And once it reaches that limit, it'll close that file and then write a new file. So that's a good way of basically managing file size, again, without having to necessarily repartition and introduce an additional shuffle step. So again, another important thing is understanding the Spark UI and leveraging the Spark UI to help you in your processing. So it's one of the first places I go to understand what's going on with the job and where there might be potential bottlenecks. So it's important to understand things like identifying where are stage boundaries, right? Where are the shuffles happening? Understanding like how to use the metrics, right? Are your predicates and column pruning getting pushed down to your data source appropriately? How large are your shuffles? Are you seeing a lot of spill happening? So I wanted to go over some examples. So here's one. This is using data sets. So this is a Parquet data set that's, again, got 10 million rows. So this is using the dataset API in Scala. So we have an input case class, output case class. We have some sort of function that's doing a transformation, right? And so then we load this data set, we convert it to a data set of this input case class, we apply our map operation, and then we filter on what's a column within the source Parquet data set. So the assumption would be, again, like I talked about earlier, is that you can use predicate pushdown and filter the data set as it's getting read in from storage. But if you look at the query plan here, you can see that it's actually loading all 10 million records, and the filter to basically less than 70,000 or 700,000 records is happening towards the end. So what's actually happening is because we're using the dataset API and we're applying the filter after our map transformation, that map operation is basically opaque to Spark. Right? We're taking some input data, we're doing something, and then we're outputting some data again. So Spark doesn't understand what happened to that ID column, right? It could be something completely different. It could be the exact same value that came from Parquet, but Spark can't understand that, right? Because it can't see into your data set transformation. So in this case, it's almost like it's breaking the lineage from the original Parquet column. So in this case, you want to consider your order of operations when you're using the dataset API, or you're doing any sort of map operation on a dataset, right? So in this case, right, if you would have moved the filter before the map, then it would have filtered the data directly in Parquet, and then you would have only fed in fewer records to your transformation. Another thing I tend to see now and again is with Python, people moving from like DataFrames back to RDDs and then back again to DataFrames. And this is something that I really don't recommend One is using the PySpark API with RDDs. It's a much slower path than DataFrames. You're also, again, breaking the lineage from the source data set. So if you notice here, this query plan, the first step is basically an existing RDD step. So that's basically just saying, we have some RDD that was turned into a data frame, and then we're doing some operations on it. But basically, we've now lost all that useful information that we would normally get with the Spark data frame SQL plan to understand what's actually going on behind the scenes. And then again, you can see because I'm applying this filter after having converted to an RDD, I've lost that predicate pushdown. So basically, again, you lose the predicate pushdown, the column pruning, and again, the less efficient PySpark RDD interface. So for SparkR, this is another thing that I've seen from time to time from SparkR users. So SparkR, if you're not familiar with that, it has a couple APIs to essentially distribute your R code, right? So you can think of your R code as UDFs. And there's there's four main interfaces. There's dapply and gapply, and dapply collect, gapply collect. Okay, so dapply is basically, it's like a map partitions. It's taking your UDF and applying it to each of the partitions. So, and the way it works is you specify your input data frame, you specify your UDF, and then you specify the output of the schema. So it knows how to convert the result from your UDF back into a Spark data frame. So what's happening here is you'll notice this deserialized to object. This is where it turns the data frame from the internal tungsten format into a format that it can then exchange to the R process. And then it's processing it, doing the map partitions. And in this case, what I have is I have three steps. The first step is calling the UDF. The second step is calling a filter using Spark SQL API filter. And then the third step is applying another UDF. So if you notice, it's doing this deserialization, map partitions, and serialization step twice. And then the filter's in the middle. So what you can actually do is just combine them in a single step, right? And just do it all within one SparkR UDF and avoid that loop of going back into Spark, deserializing the data again, and then feeding it back into R. One thing I see a lot as well is self-joins. So I see this a lot with, especially like, again, people maybe coming from like single node pandas, where things like self-joins are probably not as expensive, right, compared to doing it in a distributed framework. And so typically this is done maybe to do like row shifting, or you have like a self-referencing data set. But one important thing to keep in mind here is that what Spark is going to do is it's going to treat those two data frames, even though they're coming from the source data, they're two distinct data frames to Spark. So it's actually going to read the data twice and then do the join. So you're basically, any transformations that you had to the initial data set, to the initial data frame, you're doing twice, okay? So obviously you could do things, maybe like, cache it and stuff like that. But, there's other options in most cases. You could do things like a flat map or explode. I mean, it'll depend on your use case, but you need to consider that if you have any of these types of operations. Another one that's somewhat related is repetitive unions. I see this sometimes, again, where people are like maybe integrating with, like scikit-learn or things like that, and they're maybe trying to do like cross-validation. So again, they have an initial data set, and they basically want to make multiple copies of the same row, applying a transformation to each version of the row. And they're doing this in a loop, and then they union all the data frames together, and then they run their model. So the problem here is, again, you're reading the same data multiple times. You're also increasing the number of tasks. So if, for the number of splits for each of those data sources, you're increasing that by the number of unions that you're doing. So in this case, I'm tripling the number of tasks required for my job. And in some cases, that can actually impact Catalyst pretty badly in terms of the complexity of the query plan. So real quickly, in terms of UDFs and datasets, please, please, please learn the built-in functions. I can't tell you how many times I see people writing Python UDFs for doing like date parsing, string, like doing substrings, or like array manipulation. All that stuff's in Spark already. There's like a bunch of really smart engineers that spent a lot of time on those built-in functions, and they're optimized. They're using code generation. They're going to work a lot better than any PySpark UDF that you can write yourself. Right? Use what's there. If you absolutely need to use a UDF, then as you saw Reynold mention this morning in the talk, consider using the Pandas UDFs. Those are going to perform much better. And then again, filter and project early, right? If you're using things like datasets, try to do that as early as possible to make sure that you're reducing the amount of data that's flowing through your application. For SparkR, we have another great blog that talks about like a lot of the improvements we've been able to do to SparkR, in some cases up to 100x performance improvement. And finally, how can you learn more? Again, spend time to understand your query plan. Right? It's important for you to understand what your transformations and your actions in Spark are actually, how they're actually getting applied and run by Spark itself in the physical query plan. And if you're not sure how something works, the great thing about Spark, it's open source. You can go to the code, right? You can read how Parquet is read. You can read how CSV is read, right? That's invaluable to understanding what's actually happening within your own application. All right, with that, thank you. Any questions?
Would you gzip Parquet or not?
So yeah, so Parquet, because of the way Parquet is stored, it is actually splittable, right? So because of the row groups. Now in Spark 2.2, Snappy is the default compression. And so I think what the engineering team found is I think Snappy was just a better option for Parquet, I think due to performance.
Okay. I like to use datasets because they are type safe and try to use them most of the time. So one thing I learned is that I have to be careful when using filters to move them at the right position. What are other things that I have to care more about than when I just use DataFrames?
So one thing that you'll notice in the... So if you notice here, there's this one-step deserialize to object, right? So what has to happen when you're doing your dataset transformations is, you have a Java Bean or a case class, right? Scala case class. So Spark needs to deserialize from the internal tungsten format into that case class in order for your transformation to run. So I think one thing is just to be aware of any like the size of your case classes. So you may not actually be using all the columns within your case class if you're doing like a map potentially. So it may be worth looking at your task statistics to look at things like garbage collection time and things like that might be impacting performance. But I think the biggest issue is just being aware, like you said, of like the filter, right? Being aware of that you're not necessarily pushing the predicates down to the source.
You showed predicate push down for Parquet, but does it work for something else than long? Because last time I tested, the filter on the row groups with the min-max filter only worked on long, but string, dates was not working.
Yeah, I think with later versions of Spark, I think they've added additional data types.
Okay.
All right, let's get one more question.
In terms of this bin packaging, so is it something like it happens automatically, or
yeah?
I mean, how do I know it's happening basically? So, because sometimes we are using like if you see like many files and which are like 20 files of 1 KB, we try to do a coalesce and have it in one. We do it like externally. So, if I understand correctly, we should not do it, or
So what's happening, it's actually logged. So you can actually look at your driver logs. When you define a data set and load that data set, it'll actually log basically how many files and then how many partitions it's packing them into. Now, having said that, you definitely want to still consider compaction for storage, right? Because it's still having to open a file and read that file. So there's still a cost of reading multiple files, but your partitions as your Spark job is running will be reduced. You're not going to get one partition per file. It'll do the bin packing. So the bin packing is happening automatically, but you still want to consider doing compaction if it's a data set that you're repeatedly hitting against. It's just that in your Spark job, when you're reading that data, you don't necessarily have to worry about coalesce.
All right, so we're past time, but Silvio will probably hang around for a little bit, and you can come up and ask him questions. But thanks again, everyone, for joining us. Let's give him a round of applause.